In this video, we'll take a look at the transformer model that we'll be using in Lab 7. In particular, we're implementing the transformer's attention mechanism. The goal for this lab is to use a transformer to translate sentences from Spanish to English. Unlike in Lab 6, where we predicted what came next in a single sequence, we will have two sequences, a Spanish input sequence and an English translation as our output sequence. We will also be working at the word level rather than the character level, so our inputs are sequences of word embeddings, and our outputs are sequences of next word predictions. In Lab 6, we used an RNN to deal with sequential data. We could use RNNs to tackle translation, but we're using transformers. Instead of having memory like an RNN, transformers take in all inputs at once. Transformers are generally more powerful and much more parallelizable than RNNs. Because we have separate input and output sequences, we'll use the encoder-decoder model. Our encoder extracts data from our input sequence to create a context vector containing the meaning of the input sentence. Our decoder takes in the words we've predicted so far, as well as the context vector, in order to output predictions for which word comes next in the output sequence. Both the encoder and the decoder are split into various stacked layers. Each layer takes in a sequence of embeddings and outputs a same size sequence of new embeddings. Encoder layers transform each embedding to contain information from the whole sequence using self-attention. The decoder layers do the same thing for the output sequence. The decoder layers also take in the context vectors produced at the end of the encoder's model and mix that information in with the output sequence information using encoder-decoder attention. There are other operations performed in these layers, like the feed-forward layer, which are just a few linear layers with ReLUs in between, but attention is the only operation that combines information across word boundaries. That's why attention is the most important part of the transformer. Attention allows the network to learn to focus on different parts of its input. In encoder-decoder attention, we describe the words in our output sequence in terms of the input sequence. This matrix shows encoder-decoder attention on English to French translation. Each row represents a word in the given output sequence in French, and each cell in the row represents how much each input word in English corresponds to the given French word. Bright cells mean higher attention weights for that input, and we see that this matches with English-French word pairs. Most of the words line up along the diagonal, but we see this part of the diagonal is inverted, and this is because French and English put their adjectives on opposite sides of the noun and in opposite order. Also, the French sentence is one word longer, using three words to say was signed. With encoder-decoder attention, these grammatical differences don't cause any issues, and our network can learn to do all of this with backpropagation. Encoder-decoder attention is pretty straightforward. We need to know our input sequence, our original sentence, in order to know what our output sequence should be. We need to know what the original words were before we can translate them into another language. Self-attention is a bit less intuitive. With self-attention, we want to rewrite each word in a single sequence in terms of all the words in the exact same sequence. For the encoder, it's the input sequence, and for the decoder, it's only the output sequence. Now, why would we want to rewrite a word in terms of the other words in that sequence? Each word has its own definition, which is implied by its embeddings. But words can take on different meanings and different functions in a sentence. For example, in this sentence, here we have the word it, which is a very vague and very general word that could refer to any single thing. But in this case specifically, we can see that our network has learned that it refers to the animal specifically. And it's also important to our network that it's the animal that didn't cross the street. But with this, we're able to know what it means and what function it plays in the sentence rather than just using the vague definition of the word it. So self-attention allows us to use the context of the entire sentence to understand what each word means in this particular sentence. Before we talk about how attention works, let's talk about what we input and output for the attention function. Attention takes in 3 inputs: queries, keys, and values, which are all linear transformations of our input encodings that have been passed into the layer. For our encoder-decoder attention, which is these bottom 2 here, the queries, keys, and values all come from the same source, which is the embeddings of the layer directly below it. But for our encoder-decoder attention up here, the queries come from the layer before it. In other words, they come from the information in the output embeddings and represent our output sequence. The keys and values for encoder-decoder attention come from the input sequence. In particular, they come from the output of the final encoder layer, which will be context vectors for these that encode the meaning of the input sequence. Our query, key, and value tensors are all going to have the same dimensions. They're going to be some batch length by sequence length by their embedding dimension. But some of these dimensions will have different values. In particular, the embedding dimension is a hyperparameter that we choose. In this case, we're going to choose for them all to be the same, but in general, the queries and keys just need to have the exact same embedding dimension. As far as the sequence length, the queries are going to have their own sequence length, and the keys and values are also going, since they represent the same sequence, they will have the same sequence length. But in self-attention, they all represent the same sequence, so they will all have the same sequence length. Once we perform attention, our output is going to be a new sequence of the same size as our queries. So basically, you can think of it as we're trying to rewrite our query sequence in terms of our value vectors. For self-attention, we're rewriting each word in the sequence coming from the layer below in terms of itself. In encoder-decoder attention, we are rewriting our output sequence embeddings in terms of the input sequence embeddings, specifically the context vectors that our encoder is producing. This is our function for scaled dot product attention. Notice that there are no layers or parameters. This is just a pretty simple deterministic function. All of the learning that occurs outside of this function. And the first thing we do in this function is we multiply our query and key matrices across their embedding dimensions. This allows us to determine how similar each query, which represents a given word in the query sequence, is to each word in the key sequence, which will represent a word in our key value sequence. We scale this, the product of this multiplication by the square root of their embedding dimension size, and this is just so that the softmax just doesn't get very large inputs, because that could cause overflow and give us some pretty bad gradients. We then apply masking where appropriate, and we'll talk about masking a little bit later, but for the sake of the lab, the masking code is already given to you, so you just have to apply it there. After masking, we are going to softmax this matrix across the dimension that represents the key value sequence, so that we turn our scores of similarity for each query word into percentages. we then multiply this matrix by our value matrix. And we end up rewriting each query word as a linear combination of our value vectors for each word in the key value sequence. It's not enough to just perform attention once per layer. That would be like performing convolutions with a single filter. We want to be able to find more than one useful feature per word. This is what multi-headed attention does. Each attention head acts as a separate attention filter, focusing on different features in our sentence. Here, we take in 3 inputs, which we're going to transform into values, keys, and queries for our scale dot product attention. In this case, they will just be from the sequence, or in self-attention, these will be from the sequence, or from the output of the layer below. And so these will end up in self-attention, the value, key, and queries that come into multi-headed attention are just going to be 3 identical copies of the same thing. But with encoder-decoder attention, again, our query is going to come from the embeddings of the layer below, and our values and keys are going to come from our encoding layer. And so they represent our input sequence. So now, because these are just embeddings of the sequence, we need to transform them into something that our network can actually use. So we use some linear layers to transform these sequences into functional keys, queries, and values that our network can use to perform attention. And so this is where most of the learning for attention takes place. Notice that each of these inputs need to have different linear layers with completely separate parameters, so that our network can learn to differentiate them into their respective roles as keys, queries, and values, instead of just transforming them all into the same thing. Notice also that here we have several heads, and each attention head also has its own separate linear layers. These are not just copies. They have their own parameters, and they're completely separate layers. And that allows our network to learn how to, or to learn to focus on different aspects of the sequences coming into the attention. So in all, you'll need 3 times the number of heads, linear layers, for our inputs. So once we pass these sequences into our linear layers, we get out a trio of keys, queries, and values. Then we pass them into the scale dot product attention function, which we talked about in the previous slide. And then that's going to give us a single output tensor that is going to be batch size by the sequence length of the query by the embedding length. And so we're going to do this h times, one for each head, and we're going to concatenate all of those tensors together. And in particular, we want to concatenate them together by their embedding dimension, because we want to combine sort of the knowledge that we've gathered from each word, rather than doing it along the sequence dimension, which would be basically duplicating the sequence several times, or along the batch dimension, which would be basically performing different tasks at the same time. So we want to concatenate along the embedding dimension. And then, of course, we're going to pass it through another just simple linear layer, and then we will get our output sequence for our attention module. And notice that the only difference between self-attention and encoder-decoder attention are the input sequences that we pass in and where they come from. We don't have to account for these differences when we're creating our attention functions. There is actually one difference that we have to account for, which is masking. Now, we've already done this for you. We already provide the code, and we've already set up the transformer to apply masking as needed. But despite that, it's pretty important to understand what masking is going to do anyway. To understand how masking works, we need to understand how recursion works with our transformers. A transformer has no memory, so it's very unlike the RNN. So instead of having to pass in each input one at a time, we can pass in all the words in our input sequence that we know of through the network at once. Since we know the entire input sequence already, we can perform the encoding step in a single forward pass through our encoder model. We just pass in our entire input sequence into the encoder model at the beginning, and we don't have to do any recursion there. Decoding is going to be a little bit different. So during test time, we don't know how long our output sequence is, and we don't know what our output sequence is going to look like, right? When we're testing, we don't use the label that has the correct translation. So this means that we have to perform one forward pass of the decoder per word in our output predictions, just like an RNN. So we have to iterate over it, predict one word, pass it, add the word to the sequence, and then pass in the entire output sequence that we've already guessed in through the decoder again to get the next word, and so on. Now, this recursion works, but it's pretty expensive. And in training, we already know what the whole output sequence should be. In training, just like with the RNN, instead of using our output predictions to feed back into the network, we only use the actual correct next word in the sequence. So because we know our entire correct output sequence, right, we have the label for training, we know how to get our losses. We can pass in our entire output sequence at once and then use whatever they output to get each loss in the sequence. But there's one big problem with this, and that is if we have our entire output sequence, our network could very easily learn to predict the next word just by looking at the current word and looking one step to the right of it. Now, this is not only cheating, but the big issue with this is that we won't have this option to cheat when we're testing because we won't have the correct output sequence. So we'd end up learning something that is completely useless. So this is where the masking comes in. When we have our sequence, our two sequences here in self-attention, so it's two copies of the same sequence, what we do is we are going to mask the values such that each word cannot look at any word that comes after it. So for example, in this sentence, we have the start character, and then we have I am fine. So if we're at am, we don't want am to be able to just look forward and say, okay, the next word's fine, so I need to guess that the next word's fine, right? So instead, we just mask it, so we put a 0 there, which actually, before we do the softmax, we put it as -infinity, which once we do the softmax will become 0. But we put a 0 there, so none of the information from fine can come into M when we're performing attention. And since self-attention is the only time that we're sort of mixing this information across the word boundaries in the same sequence, by masking, we can effectively prevent a word from seeing any word that comes after it. So basically, this allows us to basically have the same amount of information for each word that we would have had if we would have performed training recursively, so passing it in one word at a time. And so this allows us to perform training in a single step, rather than having to do it recursively. With your attention coded up, you've done everything that you need to do in this lab, except for training and generating output. If you did attention right, the output predictions should be somewhat reasonable. If it's completely off the mark, the issue will be with the implementation of your attention module. Every other part of the transformer should already be implemented correctly, and you shouldn't have to change any of that. But you should note with the output that you won't really get perfect output. The biggest issue here is that the general conference dataset we're using is very noisy. So you'll see some mismatched English and Spanish pairs, which makes learning a little bit more difficult. It also has a pretty difficult time with numbers because English and Spanish page numbers and hymn numbers are different, so it never learns to translate the numbers correctly. But generally, these outputs should be pretty reasonable. It may have some repetitions or use the wrong word every once in a while. But these sorts of outputs are generally what we'll be expecting here. And as long as you've done your attention module correctly, you should get something similar. So that's it for Lab 7. If you know what you're doing, this lab should be pretty quick, but it can be really tough if you're struggling to understand attention. If you're still struggling and need a better understanding, the best resources for this lab are in the readings that we've had for this class. The Illustrated Transformer is a blog post that has some great visualizations for how attention works, and it goes through it step by step. So hopefully that'll be pretty good and easy to follow. The paper, Attention is All You Need, is the paper that proposed the transformer architecture. It's definitely a lot denser than the blog post, but it does have a lot more information, and its section on attention should be very helpful for this lab. Good luck.